Hello, my name is Chris Schmidt, and I am presenting GOES-R ABI Fire Detection, Performance of Updated Operational Algorithm. I'm a researcher at the Cooperative Institute for Meteorological Satellite Studies at the Space Science Engineering Center at the University of Wisconsin-Madison. I am the primary algorithm developer for the GOES-R fire detection and characterization algorithm. I've been doing geostationary fire detection since 2001 when I started assisting Elaine Prinz on development work for the GOES 8 through 15 wildfire automated biomass burning algorithm. ABI fire detection. The Advanced Baseline Imager is the imager on the GOES-R series of satellites that was first launched a few years ago as GOES 16 and has been joined by GOES 17. The Fire Detection and Characterization Algorithm, FDCA, is known as Baseline GOES-R Fire Detection Algorithm. It is based on the Wildfire Automated Biomass Burning algorithm that was used operationally for the previous GOES satellites. Product resolution is 2 kilometers and provides fire detections, fire radiative power, fire size, and fire temperature. The algorithm is contextual, but there are some fixed thresholds involved. Given its legacy as an algorithm developed for the previous generation of GOES satellites, it does not take full advantage of ABI's capabilities. NOAA runs the FDCA on the 5-minute CONUS and 10-minute full disk sectors only. On the right, we have images from August 19, 2020, from 6 a.m. Pacific to 5 p.m. Pacific every 5 minutes from the CONUS scan on GOES 17, showing true color imagery generated with a program called Geo2Grid, which is available as part of the CSPP Geo package available from SSEC. In this image, you can see the massive wildfires that were active in California that day, including the smoke plumes moving in various directions depending on the level at which they were present. Users and known issues. The FDCA has a wide range of current and potential users, including but not limited to aerosol modelers, emergency managers, NWS forecasters, corporations, and more. The various user groups have a range of needs, some of which conflict with each other. For example, NWS forecasters are typically looking for the earliest possible alert of a fire, and will look at the raw imagery to verify what the algorithm produces. They are willing to trade a reasonable number of false detects for higher sensitivity to smaller fires. Emergency managers and many private users, such as utilities, have similar requirements. Hazard mapping system analysts mainly review the fire detection data from GEO and LEO platforms. A large number of false positives creates a large burden for their work. Aerosol modelers want a consistent record over a large area and between different satellites. Tracking the energy output of fire events allows for better modeling. The known issues include false positives due to reflected sunlight off of water clouds, some surfaces, and recurring sources like solar farms and petroleum facilities. Low sensitivity leading to some missed detections, particularly at night. And like almost all fire algorithms, there is no use of the temporal dimension of ABI data. In other words, it is not a change detection algorithm, nor are any existing operational fire detection algorithms. How does ABI see fires? ABI is a 16-channel imager, which has bands ranging from 0.47 microns, basically blue light, all the way to 13.3 microns. This loop is from the East Troublesome Fire in Colorado on the 21st of October through the 22nd of October. It shows all 16 bands from ABI, and they are scaled to the minimum and maximum within that box centered on the fire. This is done to maximize the contrast and highlight when you can see the fire. Fires are black body emitters essentially, and they'll emit across a broad spectrum of frequencies. And you can see that in this loop, where the fire appears in many bands, not just the 3.9 micron that is best known for fire detection. This fire was sufficiently intense that we actually saw a signal in the 0.64 micron, aka red band, at night. It was only at one time step, but still, that is an incredibly hot fire to be detectable at that band. As you could see, it was mostly dominated by noise at other times. The Kincaid Fire. On October 23, 2019, at about 9:20 Pacific Daylight Time, the Kincaid Fire started in Sonoma County, California. The Alert Wildfire camera at Barham near Santa Rosa, California, captured the start of the fire. It appears that a light on the horizon went out when a power line fell between 9:19:51 and 9:19:54 p.m. PDT, the same event that apparently started the fire. The fire intensified very rapidly. GOES 17 picked up the first signs at 9:21 PDT, and by 9:25 PDT, the FDCA had detected the fire. Here we have the Alert Wildfire camera loop from 9 to 10 p.m. PDT showing the start of the Kincaid Fire. We also have ABI data centered on the Kincaid Fire. The panel on the left is the 3.9 micron mid-wave infrared window band, known for fire detection. It is set to a constant scaling. 11.2 micron band, long-wave infrared window, used for the background and fire detection, also set to constant scaling. 3.9 micron minus 11.2 micron radiance difference in 3.9 micron space, set to dynamic scaling to enhance contrast, is used to show the extra energy in the 3.9 micron band. It is done in 3.9 micron space to make it more directly comparable. The FDCA mask, the algorithm output indicating decisions about each pixel, shows when the fire was detected by the algorithm. The fire FRP, algorithm output of FRP, for all detected fires, is shown as dynamically scaled. Here we've centered on the two images bracketing the disappearance of the light on the hill and the start of the fire. They are separated by only 70 seconds. Mesoscale scans are typically 1 minute apart, although sometimes the time varies slightly due to scheduling changes required by other scans. You can see that the energy change is very small in the 3.9 micron band as well as the 2.25, where it shows up more obviously because it's nighttime. This does show the fire was rather intense at that time. As before, these panels were enhanced to show contrast. The East Troublesome Fire. On October 21, 2020, the East Troublesome Fire in Colorado underwent rapid intensification. This example demonstrates consistent detection, but also the low sensitivity causing the algorithm to miss some fire pixels. The four panels are Geotogrid True Color, 3.9 micron midwave infrared window. This one is scaled from 250 to 400 Kelvin to show the entire range of the fires. FDCA mask, the mask showing the fire detection algorithm's determination about the pixels and its classifications of them. As you can see, they vary in color from red to orange to yellow to cyan. And Fire FRP, algorithm output of FRP for all detected fires, where 0 megawatts is black, 1000 megawatts is red, 2000 megawatts is yellow, and 3000 megawatts is white. You can also see hints in the 3.9 micron panel of reflection of 3.9 micron radiation off of water clouds to the north of the Troublesome Fire. Recent changes. The FDCA underwent a major science update that went operational on July 25, 2019 for GOES 16 and GOES 17. This update reduced the number of false positives and raised the true positive rate quite a bit overall. These results come from the deep dive analysis in which FDCA data is co-located with Landsat fire detections. The use of very high resolution satellite data for comparison provides the best truth dataset possible. This technique was pioneered by Wilfred Schroeder. The changes included elimination of scaling factors that were leading to a large number of false fire signals and a reduction of overall sensitivity, among others. The lowest possibility fire category, category 15 or 35 if you're looking at the data, showed a tremendous drop in fires detected once these improvements were in place. Loop heat pipe mitigation. GOES 17's active cooling, its loop heat pipe, failed, and mitigation measures have been taken at the algorithm level and by reducing the scanning frequency at peak heating times to improve data fidelity. Fires mitigates the issues by creating a new hybrid long-wave band from two others which fail at different times during the heating cycle, specifically the 10.3 micron band and the 11.2 micron band. Typically, the algorithm only uses the 11.2 micron band. In order to create the hybrid band, the algorithm takes the radiance difference in 3.9 micron space for both of those bands and selects the pixel that has the smallest difference to the 3.9 micron band. The purpose of this is to reduce the noise as much as possible. It does reduce the scientific fidelity of the data. However, the goal was to retain as much fire detection capability as possible during this period of night over the western U.S. Not fires, solar farms. 4th of July 2019, Mode 6 full disk, 17 to 20 UTC. As mentioned earlier, solar farms can cause false alarms in FDCA data. These images cover a swath of California and Nevada from just north of LA and east past Las Vegas. Two of several solar farms are highlighted. The Topaz Solar Farm in the west, yellow circle, and solar facilities near Las Vegas, Ivanpah and others, red circle. The extent in band 7 is much greater than in the shortwave bands, likely due to remapping and diffraction. Because the shortwave bands are not available at full resolution, but instead averaged into their surroundings, using a threshold with them to screen these sites may be difficult. ABI Sensitivity to fire signals. Single-frame algorithms are limited in their sensitivity. This example is of an apartment building fire in Madison, Wisconsin on May 18, 2020. The two-story building was partially burned. The fire signal is very weak, hard to identify even by eye. It illustrates the sensitivity of ABI to the energy from fires, but also the confounding effects of solar reflection off of water clouds. The reflected signals are larger than the fire signal in this case. Here we have the red visible band, the 3.9 micron midwave infrared again, dynamically scaled of course, the 11.2 long-wave infrared band, dynamically scaled yet again. We also have the radiance difference in 3.9 micron space again, also dynamically scaled. And we have the 3.9 difference in 3.9 micron space, minus the rolling average of the last 5 frames to simulate a temporally enabled algorithm. As you can see, the fire signal is very weak and only shows up at 1821 and 1826 UTC, and we only know for sure it's a fire because we know the fire was there. Looking ahead, there are short-term improvements planned for the FDCA and longer-term plans for a next-generation fire detection algorithm at SIMS. NOAA and SIMS are not the only entities working on detection algorithms. There are some private enterprise efforts and other research teams doing the same. Short-term improvements. Operational implementation at NOAA expected in 2021. Improve sensitivity, lower the false positive rate, improve processing speed. Medium-term improvements. Likely to be implemented with NOAA's Enterprise Fire Detection System in mid to late 2021 or 2022. Integration of persistent anomaly database. Provide terrain-corrected fire locations and pixel outlines. Common file format for geostationary and polar fire products from NOAA. And creation of fire events that provide information about the fire pixel clusters like intensity and perimeter. Long-term improvements. There are plans at SIMS to develop a next-generation algorithm that utilizes the temporal dimension and truly integrates multiple platforms, as well as leverages all the advantages of ABI. NOAA is working on addressing the end-to-end fire problem, which will lead to improvements in the availability of fire detection data and a more comprehensive approach to fire-related products.